All right, and welcome back. So today we are going to be talking about how to compare the three types of functions we have talked about this year. We've talked about linear functions, quadratic functions, and most recently, exponential functions. We're going to be talking about how to compare them by looking at graphs, tables, and how to write equations given some data. So without further ado, let's review the year. So we are asked here on your guided notes to graph to decide whether data is best modeled by a linear, quadratic, or exponential function. So we're given these 5 coordinate points, and we're asked what kind of model best describes this data. So the best way that we can do is, especially if we are provided a graph, physically graph the coordinate points and see what happens. As we connect these points, we're going to see that the data appears to be quadratic. It appears to present a quadratic function. So we would say that this is going to be a quadratic function, or it's best described as a quadratic function because as we graph it, we see, hey, it looks like a parabola. It looks like it's going to be a quadratic function. That's one of the ways that we can compare to see, hey, of this data, which is best? Which model best represents this set of data? Awesome. We also can look at patterns. We can also look at patterns in our data to determine the correct model. So let's recall linear functions have a constant first difference in our y values. So in this case, in this table, our first difference is -3. So every single time as our x's increase, we are subtracting 3. So this would represent a linear function. Let's review a quadratic function. Well, quadratic functions have a constant second difference. So as we look at our table, we have some increases in our y values that aren't constant. But then the differences of those are constant. So the first case, we increase by 3, then by 5, then by 7. Those are not constant, but the differences of them are. So 3 to 5 is +2. 5 to 7 is +2. So that's a review on our quadratic functions. And then exponential functions have a constant ratio. We're multiplying by the same number in our y value. So we start at -2, then go to -8, -32, -128. Each time we're multiplying by 4. So linear functions have a constant first difference, quadratic functions have a constant second difference, and exponential functions have a constant ratio that are getting multiplied. Awesome. With this in mind, please work on problems 1 through 5 to determine which model best represents the given data. And when you're ready, please turn over and let's go on to the back. So after deciding which model best fits, or fits best, I should say, pardon me, you can write an actual function. And let's review those functions. We have a linear function, quadratic function, and an exponential. Remember that normally our linear functions are of the form y equals mx plus b. That's slope-intercept form. We have talked about standard form, which is ax plus by equals c, but typically we like to use slope-intercept form, y equals mx plus b. A quadratic function will look like y equals ax squared plus bx plus c. And lastly, an exponential function will look as y is equal to a times b raised to the x, where our exponent is only attached to our b value, which is our common ratio. So let's use these ideas to help us determine which model represents this data. So we're going to use the data in the table to describe how the software's cost is changing. Then we're going to write a function to model this data. So we're given computer softwares over a course of years and the cost in dollars per year. So we're given 0 and 80 as our first set, our first relationship, 172 is our second relationship, 2 6480 is our third relationship, and 3 5832 is our fourth relationship. So step 1 is to determine whether it is linear, quadratic, or exponential. So let's look at the first differences first. If we put it into a table, we can see that the first differences are not constant. So we know it's not going to be linear. The second differences also are not constant, so it can't be quadratic, which means that most likely we're going to be exponentially related. So we find that the ratio is constant. So we're going to be using an exponential model. We're multiplying by 0.9 each time. That's our common ratio. Now we're going to write the function. We know that exponentials are of the form y equals ab raised to the x power, and we can fill in some information that we know. We know that our common ratio is 0.9 because as we looked at the table, that's what's getting repeated multiple times. So we can replace that for b. We can substitute in the ordered pair of 0, 80 for x and y, and that comes by looking at our given data. Our x value was 0, our y value is 80. So we can substitute in our x and our y. So we now have 80 is equal to a times 0.9 raised to the 0th. We can simplify 0.9 to the 0th power because we know anything raised to the 0th power is 1. So that means that a has to be 80. Once we find a, we can then substitute it into our main formula. We have y is equal to 80 times 0.9 raised to the x. There is another way to find our a value that's a little bit simpler, but it only works if we have the x value of 0. Looking at our starting point, the starting data, we have our x as year as 0. So wherever our x is going to be 0, that means our a value is going to be that y value. So looking at it, we could automatically determine that, hey, our a value will be 80 because x is 0. But the guided notes go and show you how to do it in case, for some reason, you don't have an a value, right? Or you don't have your x value as 0. You can plug in x comma y and we would still end up with the same answer. But it might be a little bit more work. So if we are given a table and we are giving our data, if our x value is 0, the y value is going to be your a. That's your starting point, because that's where it's hitting that y axis. All right, great job with this, kiddos. Please work on problems 6 and 7 on the guided notes. Y'all are doing super well. Keep up the great work. Keep comparing these functions. If you have any questions, don't hesitate to let me know. I'll talk to you soon.